Hi and welcome to Podcast School. This is a video podcast on A2 Technology and Design, and we're going to be looking at the SIA revised syllabus for this, and indeed this section comes from Unit 3.7 and is entitled Boolean Arithmetic. So this video podcast is going to cover the following things: Boolean arithmetic, which will include Boolean addition, Boolean multiplication, and Boolean algebra. So let's begin by adding together some Boolean numbers, okay? And have a look. We've got 0 plus 0 equals 0. That's what we'd expect. Alright, 0 plus 1 is 1, and we've known that for a very long time. 1 plus 0 is also 1, but this is where things begin to get strange. In Boolean arithmetic and Boolean addition, a 1 plus a 1 equals a 1, and we'll see why that is in just a second. So the first three sums there I've said make perfect sense. The last sum, though, might not. Okay. Well, it does contradict the principles of addition, doesn't it? Because we would have expected 1 plus 1 to obviously equal 2, but this isn't the case for Boolean numbers. That's because when we're dealing with Boolean numbers, and remember Boolean numbers can only be 1 or 0, therefore without the possibility of there being a 2, well, we can't have it. So the best we can make a 1 and a 1 to equal is a 1. I've just said that there. There's no such thing as 2 within the scope of Boolean values, since the sum of 1 and 1 certainly isn't 0, therefore it must be 1 by elimination. Now that might seem a bit odd, but we'll see why that makes more sense in just a second. Okay. It does not matter how many or few terms we add together either. Look at this. 0 and 0 plus 1 is 1. 1 and 1 and 1 is a 1. 0 plus 0 plus 1 plus 1 is a 1. And in fact, any sum where there is a 1 will always equal a 1. Okay? If there is no 1 present, if that were, for example, 0 plus 0 plus 0, that would obviously equal a 0. And I've asked a question here. Does this pattern look familiar to you? Is there anything that this might remind you of? Well, in fact, let's get a bit closer to the actual matter. If there's a logic gate involved, what do you think it might be? In other words, what sort of logic gate does this pattern remind you of? Whereby if a 1 is present, the output is always a 1. Yeah, you got it. It's an OR gate. Remember, here's the truth table from an OR gate. A 0 and a 0 is a 0. A 0 and a 1 is a 1, remember? A 1 and a 1 is a 1. And a 1 and a 0 is a 1. You've known that from AS level. And if you look at the animation on the right, you can see that if A or B is closed, then Q will be lit. The LED will be lit. Alright? It goes off whenever A is open and B is open, but if B is closed, then it lights, and indeed, if they're both closed, it lights. In other words, there's no difference between the output state of the LED if one is closed or if both are closed. And that's kind of tying back to our Boolean algebra. In other words, the light doesn't get twice as bright when both are closed. Okay? It's just as bright when one is closed, one switch is closed. Okay, so perhaps that makes this Boolean algebra stuff just a little bit easier to understand. Okay, what logic gate then? So if that was addition before, this is multiplication. So have a look at this. 0 and 0, 0 times 0 equals a 0. A 0 times 1 is a 0, odd. 1 times 0 is a 0. Again, sorry, I said that was odd. It's not odd at all. That's normal. 1 times 0 is a 0. That's normal. A 1 times a 1 is a 1. So what logic gate does that remind you of? Yeah, an AND gate. Okay, because both have to be a 1 in order for there to be a 1 at the output. Look at the animation again. Okay, so there's the truth table. So if A and B are both closed, that's the only time that the output will be high. Okay, so we can think back to this set of values here, where 1 and a 1 gives us a 1. So something to do with multiplication here is tied up with the AND gate. Okay, so this is a bit of a review. There is no such thing as a subtraction in the realm of Boolean mathematics. It doesn't exist. Subtraction implies the existence of negative numbers. 5 minus 3 is the same thing as 5 plus minus 3. And in Boolean algebra, negative quantities are forbidden. And also there's no such thing in Boolean mathematics as division. Okay? But multiplication is valid in Boolean algebra, and thankfully it's the same as a real number algebra. We saw that earlier. It obeyed the laws that we would normally think of when we think of multiplication. Okay. I've said there, like normal algebra, Boolean algebra uses alphabetical letters to denote variables, but we always must keep them as capitals. Because they are allowed to possess only one of two values, remember 1 or 0, each variable has a complement, i.e. that's its opposite value. For example, if a has a value of 0, then the complement of a is a 1. Boolean notation uses a bar, and we're going to show you that now. So if a equals a 0, for example, then we say that a bar, this a with a bar over it, must equal 1. In other words, its opposite or its complement. And also, if a equals a 1, then of course a bar must equal a 0. Okay, and if you look at a NOT gate, then a as the input must give us a bar at the output. Okay, so Boolean addition is equivalent to the OR logic function. We saw that. So when you think of OR functions, you can think of it being addition within Boolean algebra. Similarly, if we think of an AND gate, then that's got something to do with multiplication. So multiplication and AND gates go together. And the complement of any Boolean number is a NOT logic function. Okay, that's it for now. This is the start of a lot of work which we're going to be looking at within Boolean algebra, electronics, logic gates, and it all goes on from here. So hopefully this hasn't been too much or too bad an introduction to this stuff. Okay, until next time then, bye bye.